Good morning and good afternoon and good evening to all the distinguished guests that are online together with us for this third exciting plenary session of the 29th Mediterranean Conference on Control and Automation, MED21, that is being hosted by Politecnico di Bari virtually, unfortunately, due to the pandemic. I am the General Chair, Maria Grazia Dotoli from Politecnico di Bari. I'm really honored to be here and again, welcome and thank you for participating to the conference. It is my honor today to introduce the plenary lecture, and for this I will leave the floor now to Professor Federica Pascucci, who is here with me in presence. She is a member of the organizing committee and one of the two workshop and tutorial chairs. Please, Federica.
Thank you, Maria Grazia, for your nice introduction. It's my pleasure today to introduce Professor Giuseppe Notarstefano. Professor Notarstefano received the laureate degree summa cum laude in electronics engineer from the University of Pisa in 2003 and the PhD degree in automation and operation research from the University of Padua in 2007. The same year, he joined as assistant professor at the University of Salento, where he became associate professor in 2016. Currently, he is full professor in the Department of Electrical, Electronic and Information Engineer Marconi at Alma Mater Studiorum, Università di Bologna. In 2014, was a recipient of the prestigious ERC Starting Grant, the program of the European Commission to boost excellence in science. He has been visiting scholar at the University of Stuttgart, University of California, Santa Barbara, and the University of Colorado Boulder. His research interests include distributed optimization, cooperative control in complex network, applied nonlinear optimal control, and trajectory optimization and maneuvering of aerial and car vehicles. He serves as associate editor in the most prominent journal in the field of control and automation. Today, Professor Notarstefano will give us a picture of the recent achievements in the field of distributed optimal control in complex multi-robot and energy networks. Giuseppe, the stage is yours.
So thanks so much, Federica. So let me start sharing my slides and just 1 second. Okay, so here it is. So I think you're able to see my slides.
Yes, we can.
Yes.
Okay, so before starting, let me deeply thank Maria Grazia and Laura for inviting me and the entire program committee, actually. So I'm really honored to be a plenary speaker for the Mediterranean Conference. And so I know I'm not so original, but I would have loved to be there in Apulia, especially because I'm from that region, so I love the region, and it would have been for me a really special occasion. But anyway, as I said, I'm really honored to give this talk, and thanks again, Federica, for the introduction. So today I would like to tell you something about distributed optimal control in general, distributed optimization, but with a special focus on cooperative control and robotics. Okay, and I will explain soon what I mean. So as most of you that are in this conference know, we have been working and handling complex systems in terms of multi-agent systems, smart systems. Now it has been almost 20 years. So I believe that we were one of the first communities that recognized that there was a lot of research in the area of intelligent devices, vehicles, robots, etc., that have the capability of communicating. And so in many of these applications, you can identify networks of so-called cyber-physical systems, robots, energy systems, or other devices. And in many of these applications, controls, but in particular, optimization together with controls plays an important role. And what we have been trying to do in the last 15 and more years is try to come up with a new paradigm, a distributed paradigm in which we can have robots and control systems that cooperate. In particular, today I will focus on distributed optimization, but as I said, with a special focus on cooperative control systems, so optimal control, optimal decision making. Okay, so this is the tour I will try to take you through. So I will start defining the distributed optimization paradigm. Then I will make some sort of detour because I would like to show you that a lot of research in distributed optimization has concentrated on a setup that is fairly known in our community and which is often known as consensus optimization. But I will try to show you how this setup is really suited for problems in data analytics, like machine learning, deep learning, or statistics in general, but it's less suited for control. So when you have cooperating robots or cooperating control systems like energy systems, then this is not really the right setup that you have in optimization. And then I will introduce two setups that are more appropriate for these applications. The first one is constraint coupled optimization, and the second one is a very recent one called aggregative optimization. And I will show you some methodologies that can be developed, that we have been developing in our group for these setups, with also some experiments and toolboxes that we have been developing. So let me start with the paradigm. So what we mean by distributed optimization? By distributed optimization, we mean that in some application, like the ones in cooperative robotics or energy networks that I will present today, you come up at some point with an optimization problem that has some structure. So it's not a fairly general optimization problem. It's an optimization problem that has some structure. And I wanted to visualize this structure with this puzzle. And the key point is that when you have multi-agent systems, each one of the systems only knows one piece of the optimization problem. So these pieces that you see here of the puzzle mean that you know only one part of the optimization problem. And so the idea is that you would like to solve the original optimization problem, so the whole optimization problem, using a distributed computing paradigm. Now our community is quite aware of what this paradigm means. So you want agents to be peers and communicate locally and do some local computation. So you want to exchange the computation rather than exchanging data to solve this optimization problem. Okay, so as I said, let me recall a little bit this first optimization setup that has been the first one investigated in the literature and also the most investigated one. So this consensus optimization. So in consensus optimization, what you have is an optimization problem in which you want to minimize the sum of functions, and all these functions depend on a common variable. Okay, so when you have a network of agents, if you remember that picture of the puzzle, in this case, knowing one piece of the puzzle means that each agent knows only one function fi. So if I'm agent I know function fi. If I'm agent j, I know function fj. but all of them want to minimize the sum of these functions, okay? And the decision variable is not related to the number of agents. So in this case, for example, you can have a two-dimensional variable x, but you can have a billion of agents with many functions, okay? And in this setup, the idea is that each agent starts to updating an estimate of an optimal solution of the problem. And the real goal in this setup is that agents reach consensus on an optimal solution. So that's why consensus optimization, because solving the optimization problem in a distributed way means that the agents want to agree on an optimal solution. Okay, and there have been many algorithms that have been developed. At the beginning, duality was a key tool that was used to solve these problems. Then primal dual algorithms have come up. And then also primal algorithm as the most famous one is one of the most famous, let's say, is the distributed gradient or distributed subgradient. And then later another approach called gradient tracking has given rise to several distributed algorithms. And there have been many others. So as I said, the key feature of this setup is that you want to solve an optimization problem in which all these functions depend on the same variable. Here, you don't have fi, but you have the parameters ui, yi here that give you the function fi, okay? And in particular, when you have machine learning problems, this is a really well-suited setup, because in this case, what you have is that you have many agents, each one knowing just one part of the data. So for example, this light blue processor only knows the light blue features, and this blue one only knows the other blue ones here. And all of them, for example, would like to train a common neural network, but they want to train them by exploiting all the data, okay? And of course, they want to keep their data private. They don't want to share the data with the other agents. So the idea is that you can come up with algorithms in which the agents reach consensus on the optimal parameters of this neural network, okay? As I said, there have been several algorithms that have been developed. Here, I just wanted to show you some simulation that we have run to train some neural network on some data set that is available online. And here we were using an algorithm that we have been developing. We called it GT-ADAM because it's some sort of distributed version of an algorithm that is called ADAM, that is very famous in deep learning. So what we did was to come up with a distributed version of that algorithm, prove its convergence, and then we applied it also to training of neural networks. Okay, but as I said, the key point here is that reaching consensus is intrinsic in computing the solution of this optimization problem. What I will do now is I will introduce some application scenarios in cooperative robotics and energy networks. And I will try to show you that reaching consensus there is not really what you want. There you want something different in terms of computing an optimal solution, okay? So let me start with the first example. So in the first example, let's take an optimal microgrid control. You have seen some example also in the other plenaries. So here you want to minimize the sum of terms due to the power generation of different generators, but also storage devices and so on. And then, as you can see here, let me go back just one second. In this cost function, you have a sum of terms here, sum over I, sum over I, sum over I, but all these terms depend on a local variable, ui, here, okay? So they don't depend on a common variable, they depend on a local variable. But then you have some coupling that in this case, for example, is due to the power balance constraint. And typically in these problems, you also have some other constraints that are local constraints. Okay, so I didn't explicitly write these constraints, but you can think of them as having a subscript I here. So they are local. Okay, so an interesting challenge that you may have in these problems, and that I will show in the other slides, is that you can have stochasticity in the problem due to, for example, renewables. Okay, so this setup is a setup that we like to call constraint coupled optimization, and I will formalize the setup. Another setup that is similar in structure to the previous one, it's a different, completely different scenario and application, but it's similar in structure in terms of optimization, is, for example, when you want to solve a pickup and delivery vehicle routing problem in multi-vehicle or multi-robot networks. Okay. Again, in this case, you have the sum of terms, each one depending on a local variable, and then you have some coupling in the constraints of all the variables. Let me point out here that the dimension of the decision variable now depends on N typically. So differently from the other setup, here the dimension of the decision variable grows with N. And in these problems, these are problems that are very common in operational research. You often have also binary variables, and so you can have mixed integer programs that are typically large scale. Okay, and again, this setup is falls in the general setup of constraint coupled optimization. So there are other examples and other applications in robotics. Say that, for example, you want to have a team of robots that wants to do some surveillance. For example, each robot wants to stay close to an intruder, but then at the same time, you want that the entire team stays close to a target. So in this case, this triangle means the body center of the robot. So you want the robot to pay attention to the intruders, but you want them to be close to the target. Okay. And similarly, let's say that you want to play a game and you are the defender team. Imagine to have a robotic team playing basketball. Then in this case, you want to stay close to your adversary, but at the same time, you want the team to be close to the ball when the other team is attacking. Okay. And I will show you some simulations and experiments that we have run on this scenario. So the nice thing is that if you formalize these two application scenarios, you come up with another structure, another problem structure that has been called aggregative optimization, and that can be seen somehow a cooperative version of aggregative game. So in this case, you have the sum of local terms in the cost function, depending on a local variable, and then you have another term that depends on some sort of aggregate function of all the variables. Okay, so this sigma can be, for example, the average, as we would say. Okay, so now let's move on in our tool. So as you saw, I've shown you two applications in which we can formalize the optimization problem as a constraint coupled optimization problem, and two more as an aggregative optimization setup. So let's start with the first one. So let's start with constraint coupled optimization, and let's see what kind of distributed approaches we can use. So let me formalize this optimization setup. So in general, you have the sum of local functions that you want to minimize. As I said, each function depends on a local variable. If you remember the optimal power grid control problem, you have local constraints, typically the dynamics of the control systems or the dynamics of the robots. And then you have a coupling constraint, and actually this is the one that makes the problem more challenging. Okay, so this constraint basically couples all the decision variables. And if you remember the initial picture of the puzzle, here in this case, the piece of the puzzle that each agent knows is the local function fi, the local constraint, because it knows, for example, its own dynamics, and then the local contribution to the coupling constraint. Okay, so agent I doesn't know all the other fj, xj, and gj. Now you can see immediately the first difference with respect to the consensus optimization setup. Now there is no consensus to reach. So if I'm agent 1 and I have an estimate of the optimal value of the first decision variable, I would like to asymptotically converge to x1 star, okay? And the optimal solution is the stack of x1 star, xn star, okay? So you may tackle this problem in a consensus way, so reaching consensus on the entire optimal stack, but then each robot should store an estimate that has dimension n. Whereas the most natural way is to locally store something that has only the local dimension of the local decision variable and converge to this x1 star. Okay, so a completely different meaning of solution. Okay, so what about optimal control? We can immediately see that an optimal control problem can be cast into this optimization setup. You have if you have many control systems, you have the sum of the costs over a time horizon of all the systems. Then locally, you have the constraints due to the local dynamics. For example, you have robot I that has some linear or nonlinear dynamics to satisfy. And then you may have some coupling, and typically this coupling is some sort of bounded resource that you want to share among the agents. And if you think about the setup that I've just shown, then you can recognize those three terms. So the cost, the local constraints, and the coupling constraints. So a distributed optimal control problem is or can be cast immediately into a constraint coupled problem if you have these coupling constraints. Okay. Okay, nice. Then the point is, how do we solve this optimization problem, this class of optimization problems in a distributed way? So what we came up in our group was with an approach that was somehow using the notion of primal decomposition, the paradigm of primal decomposition, but reformulated for this distributed setup and giving rise to a distributed algorithm. So let me explain what is the idea. So the idea is the following. As I was saying, this coupling constraint can be seen as a resource constraint. So this B can be a vector, but if you think of it as a scalar, then it's a total resource that you don't want to exceed. Okay, so you want to allocate resources locally to the agents, but their sum must be less than B. Okay, then what you can do with primal decomposition is to do the following. So you can split the total resource B into n pieces, so y1 up to yn. And then for each one of these yi, you can basically set up a local optimization problem in which you imagine to fix the local resource yi. So this problem becomes completely local, okay? And then what is that you have to do? Then you go back to a master problem in which, of course, you need to have the coupling constraint, but then now you have the coupling constraint in terms of resources, okay? And you want to minimize the sum of functions that are called primal functions, which are obtained as the minimization of this local optimization problem. As you can see here, when you minimize over xi, this pi depends on yi, okay? So if you go back to the literature, to the optimization literature, you find centralized or parallel methods to solve this problem. What we did was to come up with a distributed version, and the main challenge was to basically solve this master problem in a distributed way, because this problem is already local at the edge. Okay, so what is the algorithm that we designed? So we called it distributed primal decomposition. Not a lot of fantasy in the name. So the idea is the following. So you do a local update of this resource variable estimate. So in this way, and then you solve a local problem. But in this local problem, what you do is you compute a dual optimal variable for this problem. Okay, of course you need some assumptions for this problem. I will state the assumptions, but what we did also was to solve this problem in a scenario in which you may have a time-varying network in which the edges can change randomly. Okay, so why this update? So what is that? Why did we come up with this update? So the intuition is the following: if instead of putting the neighbors here, I put j equal to 1 up to n, so all the agents, this becomes a subgradient method, parallel or centralized. Okay, so what we were able to prove is that if you do some local updates, substituting only your neighbors here, even time varying, then you have a distributed algorithm and you can get convergence. So, and in fact, the result that we proved was that for this scenario in which edges are random with the probability 1, you have convergence in cost, and then convergence in the sense of every limit point converging to the optimal solution. In this case, we are assuming convexity in the problem and to an optimal solution. And we also were able to prove in expected values a sublinear convergence rate, okay, which was actually what you also have in a centralized setup. Okay, so you cannot get more. And the tools that we used was first of all some change of coordinates based on the graph that allowed us to state the problem as a blockwise subgradient problem, and then we extended the blockwise subgradient methods by allowing overlapping of the blocks. That was the road that we pursued. And you can basically look at this in our Automatica paper. These are just some numerical examples that we run on a plugin, a scheduling of plug-in electric vehicles. It's not one of the examples that I showed, but it's very similar to those examples. And we compared our algorithm with other existing methods based on primal dual approaches and dual subgradient approaches. Okay, so we also extended this approach to a scenario in which you still have a constraint coupled optimization problem, but you can think of a setup in which you don't know explicitly the structure of the fi of xi, but you can only sample the value. Okay, so that's very interesting in some applications in which you cannot really model completely in an engineering way the cost function, but you can evaluate it. Okay, so what we did was to basically combine an online cost learning routine with the distributed primal decomposition approach, and we were basically able to prove very similar results to the setup in which you know the cost functions. Okay. Okay, so if you think about the two application scenarios that I described at the beginning, so in that case, there was another important challenge in the optimization problem. And the challenge was basically the fact that the local constraint in those applications were mixed integer. Okay, so in this case, the problem becomes much more challenging because we know that mixed integer programs are NPR. And so we need to come up with other approaches. For example, in the results that I just showed you before, we were able to use the fact that we had strong duality in the problem under some assumptions on some convexity assumptions on the cost and the constraints. Okay, so here you cannot do that. So we had to try to come up with other approaches. Just want to recall you that since it's a constraint coupled optimization problem, the information that each agent knows is the same, but in this case, the local constraint set is mixed integer. Okay. Okay, so what is the idea that we came up with? Actually, we again looked at this setup through primal decomposition, but the hint, the main idea was to try to consider a convexification of this problem. Okay, So if you, instead of considering the local mixed integer constraints, you convexify them, you get a problem that now is convex. Okay, of course, you are relaxing the problem. You're not solving the problem that you would like to solve, but there is this very interesting theorem called due to Shapley and Folkman that tells you this very nice property. So the idea is the following. So say that you solve the convex version of this problem. So you have convexified the local sets. What the Shapley-Folkman theorem tells you is the following. So solve this problem, then if the number of agents or variables is much larger than, actually it holds in general, but it's very important when the number of variables is much larger than the number of constraints. So when you find the solution to the convex problem, then you are somehow lucky because you are ensured that n minus s of these variables will be already mixed integer. So those will be already fine for your solution. Now the problem is, what about the other s solutions? So the idea that you can come up with is the following. So try to use the Shapley-Folkman theorem to get many of those solutions already mixed integer, and then adjust the ones at most s that are not mixed integer. Okay. But the point is the following: if you try to adjust those solutions that are not mixed integer, then you are changing your solution, and then reasonably you will exceed the coupling constraint, because especially if you think of it in terms of primal decomposition, what the optimal solution tries to do is try to satisfy strictly tightly, the constraint. Okay, so the idea is the following, and it's not our idea, it's an idea that goes around in the literature. So you can restrict the resorts with some restriction sigma. Okay, and then solve the problem with a restricted resource. Okay, so what we did as our contribution is to apply this idea of restriction of the resource into a primal decomposition setup, and we found that it was really a key interesting idea because it gave us very interesting results. So as I said, once you have found an optimal solution for the convex problem, then what you do is that for those problems in which the solution is not already mixed integer, then you violate. You find a mixed integer solution, but you add some violation here. And what we were able to prove is that asymptotically, the asymptotic solution that you get is feasible in terms of both local constraints and coupling constraints. And the main idea is that the restriction allows you, if you bound correctly the restriction, then you are sure that those violations will not exceed the B. And then we were able to give also some bounds on the suboptimality that you get, some theoretical bounds. And now you can think of using primal decomposition, distributed actually, primal decomposition, to solve the convexified version of the problem, and then adjust locally with this strategy that I was telling you. And what we were able to prove is that you can also stop in finite time, and we were able to get bounds also in finite time. These are some simulations, and actually we were really happy when we saw those simulations, because as you can see, when you compare to other approaches, especially ones based on dual decomposition, what we got was a much smaller restriction, and therefore a much lower suboptimality in terms of solution. Okay, and if you look at the paper, then there is also an explanation of some intuition why this gives you some restriction that is somehow tighter than in other approaches. Okay, so if you remember now the microgrid control application that I showed at the beginning, that's really a constraint coupled optimization setup with mixed integer constraints. Okay, but there is another challenge, an additional challenge here. So these are all the contributions that you get in terms of power, and this is the total power resource constraint that you want to satisfy. As I said, the local constraints in this application are mixed integers, so the algorithm that I described is really well suited for this setup. But then, as I was mentioning at the beginning, in this setup, you may have also another problem, that is stochasticity. Okay, so if you have renewables, then in this case, this problem becomes also a stochastic problem. So what we did in this other work was to try to come up with some algorithm that could handle this stochasticity. And the intuition was, okay, so let's cast it into a constraint coupled optimization problem. That's easy because, as I showed you, that's the natural setup for this scenario. You have the local constraints that are deterministic, so this doesn't change anything with respect to the general setup. But now this B is stochastic in this case, and that's what somehow changes the what makes the problem more challenging. So what we decided to apply, this was really a very nice idea that Andrea, my PhD student, had, was to use two-stage stochastic optimization. And so the idea is that you can think of sampling the B, so get samples of the B. And the nice thing is that you don't need really data or a lot of data for them. You need data, but with those data, you can train a generative adversarial network, a GAN. Okay, and then using this GAN, you can generate a lot of samples and solve this problem that now is deterministic. And you can adapt the distributed primal decomposition approach to solve that deterministic problem. And for this setup, we were also able to get some bounds for the optimal solution. This is some simulation that we ran. Actually, it's some sort of realistic simulation because we took the data from an open source database from the European community. And in this setup, for example, we were considering 20 storage, 20 generators, 80 loads, 50 renewables. And the nice thing is that you get a pretty high number of decision variables. And in particular, a pretty high number of binary decision variables, which are the ones that make the problem more challenging. Okay. So what I want to mention is that we run these simulations using a software package that we called Disrupt and that we developed in the group. I will tell you something about this package later, but the idea is that you can really run algorithms in a distributed way, not just emulate distributed algorithms. And also for this problem in the deterministic case, we ran some Monte Carlo simulations. And as you can see here, as in the other simulations, again, the restriction is quite low, is 1%, as opposed to more than 200% of other approaches. And in this case, this is even more critical because, as you can see, if you use a larger restriction, a dual decomposition cannot solve the problem because the problem is infeasible. Whereas with our restriction, we were able to solve the problem. Okay, so this is the second application scenario that I showed you. And is a multi-robot pickup and delivery one. So it's exactly the setup that I showed you before. It's a well-known optimization framework in operational research. It's a mixed integer problem. And therefore, you can think of applying the distributed primal decomposition approach that I mentioned. What we did here is to design an ad hoc version of that algorithm that was customized for this setup. And what we figured out is that you can get much better, a much better algorithms that is customized for this setup with much better bounds. Let me show you some experiments and simulations that we ran for this setup. So, I start mentioning that we run these simulations and experiments using another toolbox that we developed. I will tell you something about in a couple of slides. So in these simulations, we were changing the number of robots, then the number of requests, and that's what we were getting. But let me show you a video, which I think explains much better than my words. So I hope you can see the window with the video.
Yes.
So this is an experiment that we run in our lab with 7 ground robots and 2 aerial robots. So each one of these robots has some pickup and then delivery locations. They can communicate according to this graph that you see here. Okay, so everything is distributed. So each robot is only doing its own computation and then communicating with the other robots. And then what's happening now is that the robots are exchanging messages and computing an optimal assignment. But the nice thing is that each robot is only computing its own route and meaning pickup and delivery location, and then it's moving toward the pickup and then delivery location. Here, we also implemented some collision avoidance strategy, but that was outside the optimization problem. One can think also to include it into the optimization problem. Okay, so that's it for the first setup. I hope you now see again my slides. So now let me tell you something about the second setup. This is a fairly new optimization setup. It's called aggregative optimization. So let me explain you briefly what is the idea or the scenario that gives rise to this setup. So say that you have a team of robots, and as I said at the beginning, imagine that each robot wants to stay close to an intruder. Okay, so in this case, this means in terms of a cost function that you want to minimize a term that, for example, can be some distance from the target. But at the same time, you have a target to protect, and therefore you would like the barycenter of the robot, for example, or another function of all the states of the robots to be close to the target. And you can think that to be another distance. Okay, so if you look at the entire optimization problem, you want to minimize the sum of functions, but these local functions now depend both on a local term and on an aggregate term. Okay, so in some sense, you can think of this aggregative optimization setup as a relaxed version of the constraint coupled optimization, because instead of having a tight constraint here on the aggregation, you have it as a penalty in the cost. Okay, so that's the intuition. Now, again, what do you mean by solving it in a distributed way? Remember again the puzzle picture. In this case, you can think of knowing each one of the local functions and these terms that are the local terms that contribute to the total aggregation function. Okay, and the agents, of course, communicate on a graph. Okay, so how can you solve this optimization problem? So this is an optimization problem. You can think of it as an unconstrained optimization at the beginning. So let's try to solve it in a centralized way. So what would you do to run a centralized algorithm? For example, you can think of a gradient method in which you update each local estimate, each xi, as xi plus 1 equal to xi of t minus alpha times what? Times the total derivative of this function. Okay, so as you can, how can you compute this total derivative? You can compute this total derivative as a first partial derivative with respect to xi by keeping fixed the second term. And then you can compute the second term using the chain rule. You can differentiate with respect to sigma and then differentiate sigma with respect to the xi. Okay. Now, the interesting thing here is that if you would like to compute this quantity, you have several global terms that you should know. Okay. In particular, In this case, you can compute the local derivative, but you should know this global aggregation estimate. The same here. And in terms of the second part of the derivative, this derivative with respect to sigma, that needs to take into account all the functions. So these are terms that you cannot know locally. So what is the idea that you can come up with to solve this problem? It's an idea that somehow is borrowed from consensus optimization. So to track these variables that you don't know. So this is not actually our idea. So it's an idea that we found. It's a very beautiful idea that we found in this paper by Li, Xi, and Hong, which, by the way, are the ones that introduced this aggregative optimization setup. And the idea is the following. So you run this local gradient term using these derivatives, but replacing what are the global quantities with local quantities. And then you track the global quantities with this protocol. So for those of you that know a little bit of distributed optimization, the gradient tracking algorithm uses this protocol. And you can do it for both the aggregation function and the gradients. And then what you can show is that if you run this protocol, what these guys shown is that you can get to the optimal solution in the axis. Okay. Okay, so, but what about if you have a dynamic scenario? So let's suppose now that your targets, your intruders don't stay fixed, but they move as well as your target. Okay, so this becomes an optimization problem that changes over time. So it changes with t. And so what you should do is to solve at each d the entire optimization problem. But of course, you don't want to do that. Then the idea is to do what is called online optimization. So you run an algorithm that somehow at each iteration does some steps of the solution of the optimization problem.
Giuseppe,
and then
Giuseppe, can you hear me? Sorry to interrupt. Just to tell you that we have less than 15 minutes to the end of the session.
Yeah, thank you. I think I'm, you said 15 minutes?
13 actually.
13, okay, yeah, sure, thanks. Okay, so what you can do then in the online framework, and that's what we really did, is to basically come up with a time-varying version of that algorithm that intuitively looks exactly the same, except that we added also local time-varying constraints, and then we had to do some projection here. And what we were able to do is that in terms of regret, you have this bound here, this linear regret, and in particular, we were able to use a constant step size, which means that in the static case, you have a linear convergence. Okay, there was another work that was introducing time-varying cost, not constraints and aggregation functions, and also the bound of the regret, we improved it. Okay. Okay, so let me show you some experiments and simulation that we run on this setup. So what I will show you now is an experiment that we ran, and actually I will thank my collaborators for that in a minute, on a basketball game. So imagine that you have a team of robots that is playing a basketball game. In this case, we were considering a 3x3 game. And so you have the first team that is attacking, and we implemented the optimization problem, the distributed optimization algorithm on the defending team. As you can see, the ball is here now, and so this one is helping to defend, and this one is also trying to stay closer, but then the ball changes, goes to the other player, and then this guy here wants to help the other one to defend. So this is not something that we forced, but it's something that came out from the choice of the cost functions and the optimization problem to solve, and from the distributed algorithm. And this is a time-varying optimization problem, because as you can see, as the intruders or the opponents move, then the cost is changing, as well as the constraints. And similarly, when the ball goes to another player, then again, the cost and the constraints are changing. And what you see here is basically the experiment, the experimental version of what you saw in Gazebo in the previous simulation. And this is also to tell you that this toolbox for cooperative robotics that we developed allows you really to run realistic simulations on toolboxes like Gazebo using this ROS2 environment. And it's very nice because the guys were telling me that in 5 minutes they were moving from the simulation to the experiments. They did a lot of work in coding for the Gazebo simulation, but then once the Gazebo was done, this was done in really 5 minutes. Okay. Okay, so let me go back because I'm almost done. As I was saying, I just wanted to advertise a little bit these two packages that we developed. The first one is called Disrupt, and it's basically a package to run distributed optimization algorithms. So the nice thing of this package is that differently from MATLAB, you don't have to somehow emulate a distributed algorithm with a 4th cycle. You really run the distributed algorithm with all the processors mapped into cores of a multi-core processor. So if there is some of you that is interested in working with distributed optimization, I suggest to try this toolbox because it facilitates a lot the simulation part. And then this other toolbox that we run, which is the one that we used for those experiments that I've showed you, is called Firebot, or as we like to call it internally in some sort of Italian way, Charbot. It's really a toolbox based on this ROS2 framework. It's a new framework that is well suited for distributed robotics. And what we did was to come up with a toolbox with routines, environments, and so on that allow you to run experiments and simulations for cooperative robotics. So just a couple of minutes to deeply thank my collaborators. So in particular, first of all, Andrea Camisa. So as you saw in many of the papers that I was citing, he's one of the contributors of most of these works. And actually, most of the work that I presented is part of his PhD thesis, in which he did really a lot of work. But let me also thank Guido and Andrea, in particular Andrea for being one of the co-designers of this Charbot toolbox. So the two Andreas are the one that really built up that toolbox. And then Francesco and Ivano that contributed to the other works that you saw. So with that, I'm done. I hope I'm not late, and I will be very happy to take questions. And thank you very much again for inviting me.
Thank you, Giuseppe, for your really nice, interesting presentation. And now it's time for question. And is there any question from the audience? If you want, you can write on the chat and I will read it or raise your hand.
I must raise my hand.
I see two hands, Raffaele and Paolo.
Okay, yes, Raffaele and Paolo. Raffaele, go ahead.
Okay, can you hear me?
Yes.
Yes.
The question is also in the chat. In any case, I read it by voice. From the shown application, it means that the presented framework is focused on cooperative scenarios where agents aim at achieving a common goal. Can the proposed framework be extended to non-cooperative scenarios? If yes, what are the main relations and the advantages, if any, with respect to other frameworks such as game theoretical techniques? The second application, second setup indeed shows some similarities to the mean field aggregative games. Thank you.
Yeah, thank you for the very interesting question, Raffaele. You are absolutely right. In everything I presented, I was assuming as a standing assumption that all the systems, all the robots are cooperative. And in fact, when you work with distributed optimization as the one that I presented, you are assuming that the robots want to cooperate, okay? There is another line of research, and there are several even Italian colleagues that are working on that. For example, Maria Prandini or Sergio Grammatico, that are doing a lot of research on that, in which you can think of some sort of game version of what I was saying. Of course, you have to use other tools. You have to use tools from game theory. What you prove is not convergence to a minimum, but typically you prove convergence to some equilibrium, for example, some Nash equilibrium. But yeah, absolutely. In this case, yeah, as I said, for example, in the basketball example, I think there is a lot of work to do in combining the two frameworks, because in some sense you want cooperation in a team, but you have also a non-cooperative setup because you have the opponent teams, and similarly for surveillance. So absolutely, there is a lot of room there.
Thank you.
I hope I answered the question.
Yes, fully. Thank you.
Thank you. And now, Paolo, can you make your question?
Yes, I was quite interested when you talk about the non-convexity, the problem of convexity in the first approach. Since, for instance, in some electrical power system, you have the power flow problem, where you can have a lot of non-convexity. Do you think that you always need to convexify the problem, or do you think that this approach can be in some way modified to just handle directly the non-convexity?
Okay, thank you, Paolo, because this is also a very interesting question. Definitely, handling non-convexity is crucial in this setup, and I agree with you that there are many problems in energy networks, but also in other fields in which you do want to have non-convexity. In some sense, the mixed integer setup is a special version of non-convexity that we consider. So I have two answers for what you asked. So the first one is we started to work. It's some work that we did is still preliminary, but there is a way to apply some sort of Shapley-Folkman theorem for a non-convex framework. So in that case, the non-convexity is in the local sets, but that's typically something reasonable. But we are still working on that, so you can think of doing that. In some sense, we need convexity for the primal decomposition. So in some sense, that's why we are looking for this convexification. So this is the first answer. The second answer is that using primal decomposition, and in particular this distributed version of primal decomposition, is one approach, as well as duality, and they need some sort of convexity. But alternatively, you may think of using directly some primal approach. And then in that case, if you think of using some primal approach, then you can try to do something that can work for non-convex problems. Of course, when you deal with non-convexity, you forget to find the global minimum. You look for stationary points. Let's say if the problem is constrained for like KKT points, but still, that could be an idea.
Thanks for your answer.
Welcome.
Now we have time maybe for the last question from Miguel.
Okay, hello. Thank you for a very nice presentation. I just want to ask two things. First thing, how do you relate your algorithms with distributed ADMM, alternate direction multipliers? So I think that there is some relation to that. And about control. To do robotic with optimization, you need some control algorithms or paradigm. I saw MPC described our feedback MPC somewhere. Can you comment on that, please? Thank you.
Yeah, thank you. Thank you for these two questions. Also very, very interesting. So as for the first question, so when you mention distributed ADMM, I guess that you are somehow referring to what has been produced in the literature, but for consensus optimization. So if you go to the literature and you look for distributed methods using ADMM, typically you find works on the consensus optimization setup. Actually, we did some work using an ADMM approach for constraint coupled optimization. For this setup that is suited in robotics, and that was really a very nice collaboration with colleagues in Milan, Alessandro Falsone and Maria Prandini, so that we came up with an algorithm that we call tracking ADMM. So if you go to our web pages or Scholar pages, there is the paper. It's an Automatica paper, you can look at it. As for the second question, absolutely, you are absolutely right. So in the experiments that I was showing, we were using distributed optimization as some sort of high-level framework for references, but you can think of doing something in an MPC fashion to solve the optimal control and then move the horizon and solve it again. We are trying something at the moment. We have some nice simulations, not theory, but it's promising. But absolutely, the MPC comes immediately when you combine optimization with control.
Okay, thank you very much.
You're welcome.
Okay, I think we have almost no time, so thank you very much, Giuseppe, for your really nice and interesting talk and for share with us your work.
Yeah, let me just thank one more time you that invited me, and I'm really honored, and the entire audience. So thank you very much.
Thanks, Giuseppe, also from my side. Thanks to all the viewers. And please be reminded that now we have more sessions, more technical sessions, as you know, and at 6 p.m. local time, Italian time, so Central European Summer Time, we will have the closing session of the conference. Thank you so much to everybody. Thank you. Bye-bye.
Bye, everybody.
Bye-bye.